Okay, let's welcome our last speakers, Jinsook and Emma Harvey.
All right, hi everyone. I'm Emma Harvey.
I'm Jinsook,
and we're both PhD students at Cornell, and we're very excited to be here to talk about our paper, Ending Affirmative Action Harms Diversity Without Improving Academic Merit. And this is joint work with Joyce, Zhou, Nikhil, Garg, Thorsten, Joachims, and Rene, Kizilcec, all of whom are also at Cornell. So the impetus for this work was the Supreme Court's ruling last year in Students for Fair Admission v. Harvard, which I will refer to as SFFA throughout. And in this case, the Supreme Court ruled that the consideration of race in college admissions violates the Equal Protection Clause of the 14th Amendment and is therefore illegal. Before it was banned, though, affirmative action was a practice used by selective colleges in America in which they gave special consideration to Black and other minority applicants who faced barriers to education as a result of systemic discrimination in the United States. And we wanted to explore how the end of affirmative action would impact a college's overall class in terms of diversity and academic merit, as well as individual applicants in terms of how arbitrary their chances of admissions are. And I should note that we did this analysis in the winter of 2023 and the spring of 2024. So we, at the time we were doing this, were trying to predict how classes might change. But now the first post-affirmative action admission cycle has concluded, and we actually have some real data on actual changes. And no spoilers, because Jinsook will talk about this, but we did a pretty good job predicting. But kind of beyond this, we think that the approach we're putting forward here is going to continue to be important in the future. And there's a few reasons for this. So first, there's the fact that the data we have so far, like the real data, does not paint a consistent story. And that's not actually that surprising, given the fact that different colleges had admissions policies that were different in the first place and responded differently to the end of affirmative action, so you would kind of expect effects to be different college to college. Second, the statistics that we see are all at the group level, so they don't really tell us anything about the experience of individual applicants. And then third, there's been a lot of talk about other policy changes, for example, things like ending legacy admissions, stuff like that, that you might want to be able to explore the likely impact of. So we think it's important to have an approach to estimate the likely impact of a policy change on a given institution, and that's what we will lay out here. So returning to our research questions, we wanted to predict how the end of affirmative action would impact the overall class as well as individual applicants. We, of course, cannot directly observe admissions outcomes under multiple policies. So in order to model the likely impact of policy change, we actually simulated admissions processes under different policies using 4 years of data from a selective American university. And to explain why we think that our approach represents a reasonable model of how the admissions outcomes will actually change, I am going to give a little bit of background about admissions at selective colleges. So in the simplest terms, we think that colleges try to admit applicants that display both academic merit and diversity. Neither of these are things that you can really directly observe about a person. So admission staff make guesses about academic merit based on test scores, grades, similar data, and then look at diversity of the kind of total admitted pool based on various axes, including demographics, socioeconomic status, skills, and so on. The process that they use to do this is called holistic admissions, which is just intended to be evaluating the whole applicant, so looking at things like essays, extracurriculars, potentially identity factors instead of test scores and grades alone. And this process is really hard. So holistic admissions on its own is labor intensive, and the number of applications that colleges in America receive has been steadily growing year over year. So a common tactic kind of to manage the workload has been for admissions officers to sort applicants in some way so that they can prioritize the most likely admits for review, spend most of their time there, and spend less time on the applicants that they think have the lowest chances of admission. Prior to COVID, a lot of colleges did this based on standardized test scores, but after test optional policies were put in place during the pandemic, colleges just did not have reliable access to that data. So some colleges turned to machine learning to help them prioritize applicants for review. And a standard process for doing that looks something like this. So first, colleges collect data on prior year's applications and admissions outcomes. Then they train some kind of an ML model to predict applicants' probability of admission based on the components of their application. And then they use that data and that model to run their current batch of applications to generate a predicted probability of admission for each new applicant. Finally, they sort applicants based on their predicted probability of admission. And then based on conversations with admission staff, we model them as reviewing applicants in that sorted order, and also as paying special attention to the top 20% of applicants who we're gonna call the top ranked pool throughout. So this kind of approach that we have here, it depends on the idea that this sorting algorithm, which is used to determine review order, actually impacts admissions outcomes. To explain why we think that that's like a pretty good assumption, I am going to quickly walk through the rest of the admissions process. So here are our applicants. They are sorted currently based on their predicted probability of admission, and we model the admission staff again as reviewing them in that order. So they will review an applicant, add them to the pool of accepted or rejected students sequentially. So just starting with the model, first the admission staff reviews the applicant with the highest probability of admission. They deem them a likely good fit. They move them to the accepted pool. The next highest ranked applicant actually deemed not a good fit, moved to the rejected pool. Next highest applicant, also a good fit, accepted, good fit, accepted, not a good fit, rejected. And the next highest applicant also is deemed to be a good fit. However, we have a problem. So in this case, it turns out the admitted class was actually full by the time we got to this applicant. And even though this applicant was rated just as highly by admission staff as the applicants who were actually accepted, they ended up being placed on the wait list just because they were reviewed later in the order. And so we argue that in this way, ranking algorithms can actually impact admissions outcomes, and this allows us to measure the likely impact of policy change without needing to observe counterfactual outcomes under different policies. Instead, we can just observe how the applicant ranking algorithm changes and look at the corresponding outcomes in the top-ranked pool. And so that's exactly what we do. We implement two models. One we call the ML baseline model. This basically takes all of the application information that is available, so academic profile, extracurriculars, et cetera. It includes identity variables, and it uses that to predict an applicant's likely chances of admission. We argue that this represents a likely ML implementation pre-SFFA ruling. And then we also do another model. We call this the no race model. Basically, it uses all of the same information except data on applicant race and identity. And we argue that this represents like a minimal modification of the ML baseline to comply with SFFA. I should note in the paper, we also look at other models to kind of contextualize the impact of removing race, but just in the interest of time, we're only going to talk about these two here. But actually, that is one of the big methodological contributions of this work, the fact that you could kind of like theoretically use this same approach to measure the expected impact of other policy changes, like potentially ending legacy admissions, which I mentioned earlier. And then the last thing that I will say before I turn it over to Jinsook to talk through our results is that the other benefit of this approach, we've mentioned this a little bit, is that you can use it to explore not only group outcomes that you can observe by looking at the actual data, but also individual outcomes. So in particular, what I mean by this is that you can look at the role of arbitrariness in admissions, and this part of our work really stems very directly from work by Cooper and colleagues that was presented at AAAI earlier this year. Basically, if you only observe actual outcomes, it's really hard to tell how arbitrary a decision is. But if you're simulating outcomes based on a ranking algorithm that's used in the admissions process, you can actually induce a small bit of randomness in that algorithm using bootstrapping, and then you can measure how consistent individuals' outcomes are across bootstrapped versions of the same policy, so kind of arbitrariness within a single policy. And this is important because optimally, a decision-making process is not arbitrary, especially for something like applying to college. You as an applicant want to feel like you have control over your outcomes. So we're able to explore that in our approach.
Hi again, my name is Jinsook Lee. So I'm gonna go over our result based on our research question. So the first research question is about group level. So what is the likely impact of ending affirmative action on the overall class? So as Emma well explained, we trained a model based on the different combinations of data sets, but today we're gonna focus on only two models, which are ML baseline model and the no race model. And then we measured how the top 20% of applicants poll changes in terms of demographics, focused on underrepresented minority group, and then socioeconomic status, including first generation college students and low income students. And then we also looked at the changes in academic merit, including the test scores such as SAT and ACT score, and then the percentage of top-ranked applicants who are actually admitted or waitlisted. So here's our first result. So the plot shows that the x-axis are percentage of applicants of the top-ranked pool, and then by the URM status, first generation, college students, and then low income status. So as we can see here, there is a huge drop in the URM composition in the top-ranked pool from 53% under ML baseline model to 20% under no race model. There are relatively smaller effects for both first-generation college students and low-income students. And then, as also, Emma already emphasized, I also want to emphasize that again, this research has been conducted before the first affirmative action policy applied, and then we could actually see that our predicted reduction in URM enrollment is actually similar to many selective schools, as we can see on the plot on the right. And then this is about the test score changes. Two distribution shows that there's the excluding race from ML baseline model results in increase in the average test scores. However, this is a very small change, which is based on the SAT score, which is from 1480 to 1490. This is also within the same range of 97 percentile. So we argue that the ending affirmative action does not meaningfully change the academic merit among the top-ranked pools. However, due to COVID, there were some missing data in test scores. So we also looked at the top-ranked applicants who are actually admitted or waitlisted. So we believe that the actual decisions show the admission staffs would have signed off on these applicants in real life. And then similar to the test score changes, there's also a minimal increase in the percentage of applicants who are actually admitted or waitlisted in the top. So now I'm trying to switch the gear and then talking about completely different from the RQ, which is analyzing the impact at the individual level. So we're bringing the concept of self-consistency and arbitrariness. So we bootstrapped the same ranking algorithm, but we're going to focus on only two algorithms today, ML baseline model and then no race model. And then we measure the self-consistency value developed by Cooper and colleagues in individual applicant outcomes across the bootstrapped versions. So here's the formula of self-consistency, pretty simple, where the M is total number of bootstrappings, M0 is the number of bootstrappings placed in the top pool, and then M1 is number of bootstrappings placed in the non-top pool. So on the bottom right, there is an example. So for example, individual one case, out of 100 predictions, the model predicted only M0, which is to be in the top pool, but whereas the individual two case, half of the predictions are to be in the top pool, and then another half is to be in the non-top pool. So in terms of the self-consistency value, individual one case is bigger than individual two. In other words, the arbitrariness is bigger in the individual two case. So basically, we calculated for each applicant self-consistency, and then we grouped by three groups. The first one is whether an applicant is consistently ranked in the top, and the second group is if they receive the arbitrary outcomes, and then the third one is consistently not ranked in the top. And then we compare the aggregate levels of arbitrariness across policies. So here's a result of our individual impact. So there are three groups here on the y-axis, and then the yellow bar represents the ML baseline model, and then the blue bar shows the race model. And then if we could look the first group, we also drew the dashed bar, which is the percentage of top pool, 20%. So we can see that there's only 9% of applicants are consistently ranked in the top pool under even like ML baseline model. What does that mean? It means like any given policy has a high degree of arbitrariness. And then what's even more interesting is it becomes more arbitrary to be in the top pool under no race policy from 9% to 5%. So it means that the inherent randomness plays even a larger role in deciding application review order under no race model. So here's a summary of our study. First question about the group overall class changes. The policy change harms racial and socioeconomic diversity, but the increase of academic merit is very minimal. What about the individual applicants? College admissions are arbitrary, and ending affirmative action increases arbitrariness even more. So we argue that the complaints long attributed to affirmative action will still remain at highly selective universities, even after the Supreme Court's ruling. So it means that many students will still get rejected, even though they have high or perfect scores. And this is not because from the specifics of any policy, including affirmative action, but from something fundamental issues that we have limited space, and also we also always carry some inherent randomness. So this is our presentation today. Thank you very much. And here's a QR code of our paper, and then we're happy to take any questions.
Thank you for the really nice presentation. So maybe I'm not understanding something properly, but like taking away race increases the arbitrariness. So can you talk about like how mechanically that is happening? Because I mean, you had the wait list. That was the process through which people were, being placed, and so. Does this simulation includes percentage of people for whom like race would have mattered? And so can you just kind of mechanically, like how does taking one attribute out of the selection criterion increase arbitrariness?
Yeah, I can give kind of an intuition for that. So first, just this is only looking at the ranking algorithm, so we argue that this is gonna like propagate into downstream outcomes, but we're really only looking at who is top ranked in that top 20% in the ranking algorithm, so the wait list is kind of like less relevant there. The intuition that we haven't done like rigorous testing on it, but kind of our initial exploration points to is basically this idea that the model was relying on race as a feature to top rank applicants. So basically underrepresented minority applicants with high test scores were kind of more likely to be in that top 20% under the ML baseline model. When you remove the race features, basically what happens is like those applicants are less likely to be in the top 20%, but there's not some other set of applicants who like uniformly replace them. It's kind of like in one run of the model, this subset of applicants kind of takes that spot. In another run of the model, this subset of applicants takes that spot. So there's not just like a group that was displaced that moves in to kind of fill that space. It's kind of everybody in this pool has high test scores, and so it's a little bit picking from who's left at random, if that makes sense.
So the classification of top ranked applicants before had race in it, and so taking it out decreases the accuracy.
Increases the arbitrariness.
Okay,
Yeah.
Got it.
Yeah.
Thank you.
So accuracy and arbitrariness is somewhat different. So the intuition of this result is no matter who you are, if the model doesn't look any race, the arbitrariness is increased. So the model is less confident to make decisions. So the variance is high. Yeah.
I think we have.
Thanks for the interesting talk. I had one question about your model for like how decisions are made in the first place. So I don't quite see how the like goal of the university to make their applicant pool diverse is incorporated, or like does it not matter since you're sort of focusing on this first ranking model?
Okay, so previously in the rankings, now no longer in the rankings, and also in the decision-making process, like some of the things that you are taking into consideration when you make a decision is like, to what extent is this applicant different from other applicants that we accept? So it's kind of in that good fit, bad fit section of the model. Obviously, this is like an oversimplification, but that's one of the places where it comes in, and that's kind of like the part where in our very simplified model, we're thinking of it.
Okay, thank you.
Okay, let's give it a round of applause for our speakers.